Stop treating the integral as a formula, because an integral is not really about area. Area is only the picture. Imagine an empty water tank. Water enters through this pipe at 2 liters every minute. After 1 minute, the tank contains 2 liters. After 3 minutes, it contains 6 liters. Nothing here feels like calculus. It is only rate multiplied by time. But draw this same information on a graph. The rate stays at 2, so its graph is a horizontal line, and the 6 liters inside the tank appear as a rectangle. The rectangle is not magically water. Its height is a rate, its width is a duration, and height multiplied by width gives the amount added. That is the first secret. Area is acting as a visual multiplication machine. The geometric area is square units, but the area under a rate graph inherits its meaning from the axes. So this area is measured in liters, not square minutes.
But real systems rarely stay constant. Suppose the pipe starts slowly, becomes faster, and then slows again. Now, we cannot simply multiply one rate by the full time. There is no single height. But for a very short interval, the rate barely changes. Inside that interval, we pretend the rate is constant. Rate times a small amount of time gives a small amount of water. Repeat that idea across the entire graph and add every small contribution. Here is a question. If we use only 4 wide rectangles, will our estimate be exact? No. The rectangles miss some water and include some that was never there. But what happens if we use 8 rectangles? 16? 100? As the rectangles become thinner, the total becomes more accurate. In the limit, the gaps disappear. The accumulation becomes exactly the signed area beneath the curve. This symbol is not an arbitrary decoration. It began as a stretched letter S for sum, and that is exactly what the symbol asks us to do. The expression inside tells us the rate. The tiny dt tells us the width of each contribution and which variable is changing. The lower and upper numbers tell us where accumulation begins and ends. So the whole expression says, add every tiny rate times time contribution from the beginning up to time t. That is accumulation, and area is how the graph displays that accumulation.
Until now, we stop the graph at one fixed time, but unlock that endpoint and let it move. At every time t, record the total water collected so far. This creates a completely new function. The original graph shows the rate entering now. The new graph shows everything accumulated before now. This distinction is the center of the whole video. A high rate makes the total rise quickly. A low positive rate still increases the total, but slowly. And when the rate is 0, accumulation temporarily stops. Now comes the surprising part. Move the endpoint forward by a tiny amount, dt. How much new area was added? The sliver's height is approximately the current rate, r of t. Its width is dt. So the new amount is approximately current rate multiplied by a tiny change in time. Divide both sides by dt, and as the time step shrinks towards 0, the approximation becomes exact. The derivative of the accumulated amount is the original rate. In other words, differentiation recovers what integration accumulated.